Today we're going to do a lab to find the acceleration due to gravity. Now we expect that value to be somewhere around negative 9.81, but it can be higher, it can be lower, depending upon your location on Earth. In Vancouver, the acceleration due to gravity is larger because you're closer to the center of the Earth. In Calgary, it's a little bit lower because you're further away from the center of the Earth. We don't know exactly what we should get today, but we know that it should be somewhere around negative 9.81. Now, we always have a problem in a lab, and the problem is always phrased in the form of a question, and it needs to be specific. Because the value of acceleration due to gravity changes with location, we're going to be specific in saying, what is the acceleration due to gravity on Earth at Holy Trinity Academy, at HTA? It's different at HTA than it is in Vancouver. It's even different at HTA than it is at Foothills, because HTA is higher elevation. Now, the difference would be minuscule because of the small difference in elevation, but it would be different. Okay, the higher you are, the lower the acceleration due to gravity is. Be specific. We're measuring at HTA, so let's write that in our problem. What's the acceleration due to gravity at HTA? Now, these are your materials. You're going to list the materials in words in point form. Do not write like this. Don't write phone, comma, ball, comma. Don't do that. Okay, write phone, dash ball, etc. Right, all the materials that you're going to need. You can see that you're going to use your phone here, which is of course going to connect wirelessly to the AirLink apparatus, which is going to connect via a wire to the motion sensor. Now we have a ball that we're going to drop toward the motion sensor. What's this thing right here on top of the motion sensor? It's a little cage, right? Sometimes they call it a cage, sometimes they call it a shield, okay, whatever you want to call it there. It's to protect the motion sensor when we drop the ball towards it. That's all it is. It doesn't do anything other than protect the motion sensor. Now, a procedure, we're going to write a procedure for the first time. And remember, the procedure is going to be listed step 1, step 2, step 3. Don't write a paragraph as to what you did. List your steps as to what you did. Step 1, step 2, step 3. Now, what kind of detail do we need here? Firstly, let me tell you that you do not need to tell me all these tiny little details that are extraneous, like I broke my pencil lead and went and sharpened my pencil. Okay? That does not affect how this lab is performed. That's not necessary. What the steps that you need are the steps that another group would need in order to perform the lab from your report. So in other words, if there was a group tomorrow morning going to perform this same lab, they should be able to follow your steps and perform the lab. You can assume that they know how to use equipment. So for instance, when you say that you're connecting the motion sensor and AirLink to your phone via Bluetooth, you don't need to explain all the steps of how to connect the motion sensor and Bluetooth to, the motion sensor and AirLink to your phone via Bluetooth. You just say connect via Bluetooth the motion sensor and AirLink to your phone. Does that make sense? You can assume that the people doing the lab know how to use the equipment. Tell them what equipment to use, tell them to connect it, but you don't have to tell them how to connect it. Okay, there's certain things that you can assume like that. Does that kind of make sense? So provide for us detail enough that somebody that knows how to use the equipment and knows something about physics could perform the lab, but don't give me the kind of detail that is really silliness, like, you know, I made a mistake, so I erased it with my eraser. Right? Now, what's going to come next for us after the procedure? It's our data. You're going to collect data in the exact same way as you did for the constant velocity lab, except this time you're going to need 3 columns worth of data. You know, if you remember from that lab, you know that you had several columns worth of data when you exported your data. You're still going to have several columns worth of data when you export your data. I want you to delete all of the columns except these 3. Now remember, in the last lab, you deleted all columns except these 2. Leave the 3rd column this time. Leave the velocity this time. So 3 columns in your data. That's it for data. There's no graphs, none of that stuff for data. Okay, that's all analysis. Now, when we scroll forward to analysis, we can see that there's actually going to be 2 graphs here. The first graph is going to be, what do you think it is? Yeah, time and position. It's going to be position versus time on the x-axis. And you should expect to see for this one a curved line, because we're going to we're going to drop this ball, right? We're going to drop the ball on top of the motion sensor. It accelerates. You're going to see a curved line for position versus time indicating that acceleration. I'm not going to show you the way that it's supposed to curve. You're going to see that yourself, all right? Now the second one, what do you think that one's going to be? It is going to be a straight line, but what's going to be plotted on the y-axis? Velocity. It's velocity versus time. And that one should be a straight line. Having said that, it's not going to be a straight line like this. It's going to be a straight line like this. It's a constant acceleration, but it's a constant negative acceleration because this ball is coming from the top of the atrium down towards this motion sensor. In other words, it's moving in the negative direction. Does that make sense? Constant negative acceleration. That's okay. It's not a big deal. You're going to get the slope from that like you would if it was a constant positive acceleration. Now, in both of these, do not forget for both of them to draw your trend line. The trend line on the right-hand side will be linear. The trend line on the left-hand side will not be linear. Okay, select another trend line other than the linear trend line. Okay? You do not need to display the equation on this one. We don't care what the equation is for this one. But you do, for this one, need to display the equation. The reason is because for this one, the slope of this graph is going to represent the acceleration. And that's ultimately what we want to find, right? Is the acceleration. Make sense? The conclusion that you're going to draw from this, what is the acceleration? I state it. Say what it is. Let's say you get negative 9.6. The acceleration of this falling ball is negative 9.6 meters per second squared. The acceleration is negative 11 meters per second squared, whatever you end up getting. State what the acceleration is. And then compare it. State what it is and compare with 9.81. In other words, does it match up with the accepted value of the acceleration due to gravity? Realistically, you're not going to get exactly 9.81. If you get 9.79, okay, that's really good. And you can probably say, like, yeah, that's the same as or pretty darn close to what we expected to get, right? But what if you get like 9.66? Is that good enough? What if you get 10.32? That's pretty close. Is that good enough? In order to determine if your number is good enough, we want to calculate down here a percent difference. You guys ever done that before? Percent difference tells us how far off the value that we got is from the value that we expect. So we're going to say the percent difference is the actual value that we got minus the theoretical value, minus what it should have been. Divide it by the theoretical value. And then we're going to add these little vertical lines here. What do those vertical lines mean? Yep, yeah. Absolute value. So whether you get a positive or negative value there, it doesn't matter. You're just going to take the magnitude of it, take the absolute value of it, and then multiply it by 100. The actual value, it's the slope of the graph. The theoretical value is negative 9.81 meters per second squared. So actual minus theoretical over theoretical times 100. And if you get a number that is less than 10%, you can say, yeah, it's close enough to the theoretical value, to the predicted value that it ended up being what we expected. If you get a number that's bigger than 10%, then you would say, no, it's not what we expected. We expected 9.81, we got 12.5, a difference of about 25%, so it's not what was predicted. So your conclusion again is state the value. What did you get for the value? Secondly, compare it with 9.81 meters per second squared, and that comes from your percent difference. And finally, the third part of your conclusion is simply going to be, how do you know? So just briefly tell me how you know that the acceleration is this value and whether it's close enough to the accepted value that you predicted. Right? In other words, related to the slope of the graph and your percent difference here. All right? Now, avoid what some people did in the first lab, which was using first person. First person means I, we. Don't say we. Don't say I. I found this. No, you didn't. This was found. Okay? Don't say we did this. No, you didn't. This was done. Don't say I or we anywhere in the lab, including this conclusion, including the sources of error. I have 3 sources of error listed here. You don't necessarily need 3. If you have 2 good ones, I'll take that. 2 or 3 good sources of error. Okay, the more the better though. You also need suggestions for improvement. Avoid the following. Avoid human error. A mistake was made in calculating blah, blah, blah. Well, then fix it. Okay, that's not a source of error. Okay, you are not a source of error. Your partner is not a source of error. Avoid human error. Also avoid general things like, oh, equipment was not precise. Solution, get new equipment that is more precise. Okay, that doesn't work. I see that every time. Okay, that's not good enough. We need to be more precise about that. Okay, if you think your equipment is not precise enough, okay, tell me why it's not precise enough. And if you want to get new equipment that's more precise, be specific. Tell me what you're getting that's more precise. If you don't know what's more precise, then don't use that as a source of error. All right? So avoid human error and avoid general things. Be specific with your things. They don't have to be these groundbreaking things, but they need to be specific and good. All right, so what do you got to hand in for this one? On Thursday. You need a problem, you need materials, you need procedure, you need data, analysis, conclusion, and sources of error. So we're almost at the point of doing a full lab write-up. Notice there's a couple things that are conspicuously absent from this though. One is variables. We didn't put variables in this. And the second one is hypothesis. We didn't put hypothesis in this. Other than that, that's a full lab write-up, right? Just like you did in Science 10 and in Science 9.